video, we'll take a look at sinusoids, what makes a sinusoid, and their attributes. So what are sinusoids? Any function that can be expressed by a trigonometric sine or a cosine function is a sinusoid. Sinusoids are also known as sinusoidal functions. So how does a sinusoid looks like mathematically? So we can express a sinusoid this way. This one is what we call the amplitude of the sinusoid. This uh, expression here is the argument of the sine function, where omega is the angular velocity in radians per second. P here is the phase angle of the sinusoid in either degrees or radians. Another expression for the sinusoid is this one, where we have replaced omega here by this 2 pi f, where f there is the frequency of the sinusoid in hertz or in cycles per second. A third expression is shown here where the frequency is replaced by 1 over t, where t is the period of the sinusoid. Now, a period, take note, a sinusoid is a sine function or a cosine function. And this function is a periodic function. So it keeps on repeating every period. Now, period here is defined as the length of time it takes for the function to make one cycle. This is for how does the sinusoid looks like given its mathematical expression. So if the phase angle here is a positive, it would look something like this. While if it is negative, it would look like this. And if it is 0, it would look like this. So the difference here is where the sinusoid started. So if it is 0, we can draw it as starting at t equals 0. When it is positive, we can draw it as if it is starting before t equals 0. While if p is negative, it is we can draw it as if it started after t equals 0. So sinusoid can also be used to express current. So in AC circuit analysis, a sinusoid expresses either a voltage or a current. In this case, we have shown it to express a current. Now, as said before, a sinusoid can also be expressed as a cosine function. So here is an example. A voltage expressed as a cosine function. And their corresponding waveforms are this. So if the phase angle is a positive, we get this one. If it is a negative, we get this one. And if it is a 0, we have this one. Take note that this plot is in terms of omega t, which is actually in radians. And the offsets here are shown as in degrees or in radians. Now we can express this similarly in terms of time itself, and it would look exactly the same except that the offsets are expressed in seconds. So phi over omega here is in seconds. So take note that in our trigo days, we have this relationship. So cosine can be expressed in terms of a sine function as long as you introduce the necessary adjustments. And because of that, a sinusoid, say, expressed as a cosine function, can also be expressed as a sine function. So here we have an expression where uh, if it is expressed as a cosine function, the phase angle here is 0, but once we express it as a sine function, there appears a phase angle of 90 degrees or pi over 2 radians. If the expression as a cosine function has already the phase angle, once expressed as a sine function, again, we need to have adjustment by adding to the phase angle a plus 90 degrees, or this one. Also take note that another trigonometric relation is if we have a negative sign, we can make it a positive by simply adding plus or minus 180 in the argument of sine, one plus or minus 180 degrees or plus or minus 5 radians. The same goes to a negative cosine that can be expressed as a positive cosine by adding or subtracting these. So let's have some examples uh, to have a good grasp of what is a sinusoid. So here we're asked for the amplitude, frequency, period of these following sinusoids. So let's go over with these examples. So for letter A, so we put it in a form similar to the general form that we have discussed a while ago, and we simply compare, and we can conclude that uh, our amplitude here is 75, omega is 60 pi radians per second, and phase angle is 0. So take note that omega is what is beside the variable t. Now, since omega is 2 pi f, that means we can compute for the frequency, and that is 30 cycles per second, or 30 hertz. And also, since uh, f is equals to 1 over t, we can then compute for t, and we got here 0.033 seconds. Okay, for the second example, we have here a negative 10 sine 5t, and we can rearrange that to appear, make it appear like this. And take note that we can make the negative disappear by applying either a plus or a minus 180 degrees. Okay, so in that case, we have the following. So we have the amplitude as 10, omega 5, and P phase angle as 180 degrees. And for frequency, we will get this, and the period, we will get this one. Okay, for C, D, and E, take note that This is letter C is already in a good format, and you will note that the amplitude is 50, omega is 1000, and the phase angle is pi over 3 radians. Now, pi over 3 in degrees is that's 60 degrees because pi is 180 and we divide it by 3, so you will get 60 degrees. Now, in letter D, this is a sinusoid expressed as a cosine function, and uh, we can we can we don't need to have it uh, let's say expressed as a sine function, and in that case you will have omega as 20 or amplitude as 20 and omega as 30 radians per second. Now take note that if we're going to express this as a sine function, this will be 20 sine as 30t plus a 90 degrees here. Okay, 90 degrees. Sorry for that. Uh, so that will change the phase angle, and the phase angle that has 90 degrees. But take note that the amplitude and the angular velocity omega is still the same. Now in this last example, this doesn't look like a sinusoid, but take note that we have a relation in trigo that is like this, no? That twice of the sine and cosine is really equal to the sine of 2 times the argument of the sine. So in that case, if for example I put a 2 here, and I also divide it by 2, nothing has changed. This one is that includes the 2 can be expressed as sine 20 times 2, 40t, and then here we have 5 halves. Okay, so there you are. Um, okay, an instantaneous value of time of a sinusoid uh, refers to its value at any point in time. Instantaneous values being a changing value of in a sinusoid are expressed in lower cases. For example, if we have a voltage, these values are expressed as in lowercase. Okay. Now, since these sinusoids are periodic functions, so they keep repeating themselves, uh, an instantaneous value exists on some other time. So what do we mean by this? So for example, uh, b sub 1 is a value at t equals t sub 1, and another instantaneous value v2 exists at time t sub 2. However, the same value of v2 exists at this point in time, t sub 2 plus the period. So the value of v sub 2 keeps repeating every t seconds or every period. And not only that, there's also a value here. That's because of the symmetry of the function. So therefore, a sinusoidal function can be expressed also as this one, since if you add a period to the time, you will get the same value. Okay, so here you could also express it as this one or this one. Let's have another example about the instantaneous value. So here we have an alternating voltage given by this expression, and we're asked to determine the time when is this voltage going to be half its peak or half its maximum value. So here is the solution. So we know that peak value is really just the amplitude of the sinusoid. So we have peak value equals 325 volts. And given the angular velocity, we can get the period, and that is equals to 67.67 milliseconds. So this is the waveform. Now, so we have here the amplitude, the period, and let's assume that this point here is about half of the peak value of 325. So therefore, we need to know what is t sub 1 here, and that would be the answer. But take note that half of the peak also occurs at t sub 2, and even at this point in time, and so on. Now, so therefore, let's just limit our uh, requirement with knowing what is t sub 1 and what is t sub 2. Okay, so we simply let b as equals to half the peak. So we have this one. So that will cancel out the 325 here. And to get t, we solve for this one equals to the inverse sine of 0.5. Now take note that this one is a radian because omega is radians per second. So 377 radians per second. And if you multiply that by a second, you will get radians. So therefore, in getting this, it has to be expressed in radians. So doing that, we will get t sub 1 equals 3.39 milliseconds. Now, how do we get t sub 2? So take note that uh, this one is half of the period, and to get t sub 2, we simply subtract. And by the way, this portion here is really equals to this portion here because of the symmetry of the curve. So therefore, to get t sub 2, all we need to do is subtract from half of the period t sub 1, and that will give us 6.95 milliseconds. So that's it for the characteristics of sinusoids. And on our next video, we'll discuss the terms leading and lagging. Um, they are used to compare sinusoids of similar frequency. So I'll see you in the next video.